they give that to people. It's just on the desk. I don't know. I have normal size chalk too.
You don't like that?
No. All right. Well, so we're at 5 after, so we're going to start. Benoit, you should stay up here. I'm going to introduce you. So I'm giving the lecture today. The next 3 after that are going to be given by Benoit here. Benoit is a postdoc with Pablo. So you're covering what on the lectures again? Yeah, I think you're doing duality and some application examples. Yep. But Benoit will be your lecturer for the next 3 times, and then I'll wrap up the last 2. So. So last time we were finishing with talking about convex, trying to recognize convex optimization problems. And we wrapped up with talking about the DCP rule set, so disciplined convex programming. And this rule set is a way for the specific parser, CVX, pi, convex JL, et cetera, to be able to recognize whether your problem is convex. It lets you write problems in a slightly more general format. You don't have to think so rigidly about the standard forms and things. And I kind of had to rush through the end, and so I wanted to start this lecture by reiterating DCP. The reason I'm talking about this is not because DCP is essential to convex programming in general, but it's more that it's an example of a rule set of specific parser, and every parser is going to have rule sets like this. And so it's important to be able to understand how parsers work and use them. So just as a reminder, when we're working with optimization problems, we have the actual problem, which we write in math. We have the programming language that we're going to write in. So this is Python, Julia, etc. Depends on what you want to do. We also have the parser. So this is a library written for the programming language that lets us translate the problem that we've written in math into nice code. And so the purpose of parsers is to be very flexible so that, for example, I can just call the one norm function is less than or equal to 1, rather than explicitly having to write the linearized version of this, which is minus y I xi less than or equal to yi, and then the sum, the yi's, is equal to 1. So what a parser is going to do is it's going to make it so that these kinds of transformations happen automatically. I don't have to worry about them. So I don't have to constantly be writing into standard form. Also, these parsers are what are actually going to talk to our solvers, which are going to solve problems that appear in their standard form. And so, at least when I think about linear programming, I like to be able to think about, okay, I'm doing general polyhedral inequalities. AX is less than or equal to B. AX is more than or equal to B, et cetera, et cetera. I don't want to have to think about the mechanics of turning the crank, of changing an inequality into a LP that is the standard form, the Slack standard form. So the parser is going to turn that crank for me. And so when it comes to solvers, you should pick your solver. But if you can avoid it, avoid talking to your solver. Try to talk to a solver through a parser. OK, so the DCP rule set basically boils down to as a reminder, we have expressions and we have functions. So an expression can be positive, negative, or unknown sign. So for example, I have x squared, which is positive, minus x squared is negative. If I did a line, well, that's not consistently positive or consistently negative. So the sign's going to change. And so that means unknown. It's not both. And then they also have curvature. So the options of curvature, this is also sometimes called vexity for convexity or concavity. So we can have, so f of x can be constant. So that means it does not depend on doesn't depend on x. I can be affine. That's going to mean that basically convex combinations are exactly, of the arguments is exactly equal to the convex combination, exactly equal to. So I can be convex, which is, again, just the definition of convex here. Make sure I get that sign right. It can be concave, which is the same expression with these signs flipped, or I can be unknown. I'm trying to make a concerted effort to write bigger today because I'm doing my best for the people who are online, which I'm realizing my camera's tilted up. You can still see, good. So hopefully this makes things easier for people who are online, which means I'm going to go through a lot of boards today. Okay, and so every expression is going to be built up from atoms, and it's just a composition of functions. And so the question is, how do I compose and still check convex? So a function f of expression 1 to expression n is convex if, so first we need f is convex. And for all I, one of the following holds. Yep.
So this basically means like if you have a nested composite function, you're flattening every function, right? That's what the expressions are, right?
So, for example, I could have the function f of x, y is equal to x squared plus y squared. So that's like the actual function. But into this, I could be plugging something like ax plus b, cx plus d. I'm plugging in two expressions into this function.
Okay, but it's like recursive, right? Like
Yeah.
if you have another level, you would flatten them all into this expression 1 to expression n. And you have like a huge nested tree of expressions.
I'm not sure what you mean by flatten, but you build this up from atoms. So when DCP would check whether you're convex, it goes all the way down to the root of this tree and starts at, okay, is X convex, concave? Does it have a positive sign, negative sign, etc.? So it would start here. Does X have a known sign? Then it would apply AX plus B. Okay, that's an affine expression of X.
It starts from the leaves or the root?
Starts from the leaves, right? You have to build up from the bottom.
So basically, like the leaf, the leaf or the children of the parent node are the expressions of. If F is the parent node, the expressions are the children in this like tree structure.
So you start from the leaves and you just build backwards until you end up with just one thing that I can say. So the question is about how this tree is traversed, but so you start from the leaves and you just try to verify convexity all the way to the top. So at the end you'll end up with a big tree like this that has a bunch of components. And so if all of these start convex, if I can verify each of these is convex, that some composition of some function results in a convex expression. And this is also a convex expression, and the composition is still convex, then the whole thing's still convex.
So we should be thinking about this F expression 1, expression n thing as being at each node. Is it something we're checking? Each node is the F?
This is like the big expression. So this F expression 1, expression n, this happens at every individual step, right? So basically, at the individual step where I'm trying to check whether the composition of f of x, x, y is equal to this function, I'm trying to check whether this is convex I'm only trying to check whether f is convex as a function of the expression x and the expression y. In this example, the expression x and the expression y are the norm of ax plus b and the norm of cx plus d. I'm going to go through an example of this. So one of these has to hold. So f increasing in arg I and x per I concave. That should be convex. And then if I want to check concavity, you basically flip you flip all of the vexes basically. So concave, concave, convex. So you can flip this. If you want to see it written out, I'd look up the DCP rule set. But this is the basic idea. There's this general composition theorem that we're going to work off of. Okay, so the first example we're going to think about is this x plus y squared to the square is less than or equal to x minus y. So we're going to start from the, if we're going to be really pedantic, we're going to do this. Okay, so let's start with the basic atoms or symbols that are involved. The very bottom of this, the leaves of this tree. So what is the sign of X? Unknown. And same with Y. Okay, so the function X is just a line, and so that's obviously convex. So is the function X plus Y convex, concave, affine, or unknown? So the sign here is going to be unknown. And what is the function X plus Y's vexity or curvature? It's affine. Okay, so now I'm going to plug this affine expression into the function x squared. Okay, what vexity does this function have? X squared is what kind of function? It's convex. So, can I certify that that x plus y squared is convex? Why? I see someone nodding. So the sub-expression I put into it is, so first, f is convex, so we satisfy condition 1. And there's only one expression put into it, and that expression is affine. So this is still DCP. Okay, but at this point in the tree, so what do I have? What is my sign? What is my sign right now, according to the DCP rules? Talk about this. What is the vexity right now? It's convex. Okay, so this is an important point. Obviously, the square of a function is going to spit out something positive, right? But I never gave you the ability to change the sign here. This is a subtle point. And they update the rule set from time to time, and sometimes they work on this. So it might not be true, but it was true last time I ran this example. This sign is actually unknown. Oh, wait, actually, no. This sign is probably still positive. That's not the problem. Sorry. This is probably positive. That's not the problem I see. This is going to be positive. The problem is, okay, now I'm going to plug in, again, into the function f is equal to something squared, right? Sorry. My bad on that. What is the problem with trying to plug in this expression into the DCP rules? Exactly. X squared is not monotonic. So f isn't increasing in the argument I. But we know x squared is positive. And what is true about x squared when x is positive? It's monotonically increasing on that half, right? And so we know actually that this composition is going to be okay because of the domain that we're dealing with. So for the sake of DCP, I need to be more specific, actually. So CVX pi has this square pos function, which actually says, OK, I want the square of something that's positive. And that is actually going to be DCP. So then that means that I need to do square pos of x plus y squared. If I'm actually going to write this on a computer, I can't use the square function twice. I could use the fourth function, but for the sake of this example, we're going to do that.
Wouldn't you need to use it on the inner one? Because after you've already squared it, you know it's positive, right? You know it's monotonically increasing. It's positive.
What's the question?
Like shouldn't you use square pos in the nested one, like the inner square?
Why? So the question is whether we should use square pos the first time we take the square. Why shouldn't we do that? Square pos means that I want the square, but I know the input to the function is going to be positive. X plus y has what sign? So what do we think would happen, actually, if I called square pos on x plus y in this example, in that first one?
Does the DCP checker just say, I can't verify?
Yeah, square pos is gonna say, you need to give me an expression with a positive sign. And then finally, the final step is going to be the composition of this expression and this expression, which is just an affine combination of two convex functions, so that one checks easily.
All this square pos and this, isn't it possible to just automatically detect the positivity of the input? Like you know that shouldn't it be able to automatically parse that?
It could, I'm sure, but you could argue that I don't want to implement square in a way that checks that for you automatically, or I do want to implement it automatically, because the tree is different if you do that. Why it's implemented certain ways is kind of beyond the scope of what I want to talk about, but these are the rules you're given on high. And if you don't want to use them, you have to find a different parser. And unfortunately, it's a lot like with a programming language. You don't get to make the rules unless you want to implement your own programming language. So I'm going to do one more example. Because again, these are subtle. And when you're trying to solve a problem and you're getting a bunch of DCP bugs, it's very easy to just throw your hands in the air and be like, oh, it must not be convex. But you really want to check that you're doing things correctly. Because again, DCP implies convex, but the other way is not true. Okay, so the second one is norm max between x and 1 max between y and 2 less than or equal to 3x plus y. Can anyone spot right off the bat what's going to break here? This is going to break for an extremely similar reason as to, it's going to break for a very similar reason as to this one, but the fix is very different. Okay, so let's start with, I'll just start at max of x and 1. Also, does everyone understand the notation? I'm trying to take the norm of the vector max x1 mathematically, that's what I'm trying to do. I'm going to ignore the right-hand side because, again, it's pretty irrelevant. Can anyone tell me why this left-hand side is even a convex function? From just general composition rules. Go ahead. So the answer was I'm plugging a norm into another norm.
So it's just plugging it, and they're sort of obviously non-decreasing. I don't know, it seems sort of intuitive.
Yeah, so the intuition is that they're non-decreasing. I'm plugging in a norm into another norm. This is actually not a norm because max would have to be of the absolute values, but I'm taking the pointwise maximum of linear functions. That's convex. Yeah. And so convex, and then I'm taking the norm of convex functions. But is the norm of a convex function? So yes, they're increasing. That's one of the keys. But what's true about norms? So what I'm putting into it might be increasing, but are norms themselves increasing functions? Exactly. Like I said, it's basically the same problem. So what's going to break in the DCP rule set again, as someone in the back just said, is that these maxes are going to be more than 0, but the norm doesn't know that, and so that's what's going to break. Unfortunately, there's no norm pos function, right? That'd be a weird function to have. So let's start with in order for norm, which is a convex function, but is neither increasing or decreasing, what do I need? What am I allowed to plug into it in order for it to be DCP? What I plug into it needs to be affine, right? So that means I want something of the form norm of UV. It's less than or equal to. right? It needs to be an affine function of the input arguments, the input expressions. But if I do that, well, I've just introduced two new symbols. And convex optimization solvers are going to do exactly what you told them to. So if I introduce two free symbols, it's going to treat them like free symbols. So I do need to constrain these. How can I constrain U, for example, so that I have an equivalent set of constraints? U does have to be at least one, sure. But I need to be a little bit more than that. So here, what I'm doing is I introduce this variable u. So why can't I just do this? Let's start there. Why can't I put an equality constraint there? The rule about equality constraints in convex optimization is equality constraints have to be affine functions. And a pointwise maximum is not an affine function. So
In general, does it ever help to do that? Because it's just like, if you just replace it, it doesn't change anything, right? Or I guess for parsing purposes, it might help. Is that what you're saying?
So the question is, does this actually do anything to the problem? No, I've rewritten the constraints in a way that is completely equivalent, but it makes the parsers actually work to actually be able to use. Every parser has a set of constraints that it can actually parse into a standard form. And if you can't get them into the standard forms are very, very restrictive, and you'll spend a lot of time trying to translate problems into standard form. Parsers are a little bit more high level. They can accept slightly more general, but at the end of the day, there are still rules about what they can accept. And so from the mathematical standpoint, no, I haven't changed anything. But from the standpoint of representing it in a computer, I've changed a lot. So I can't make these equality constraints. This, though, is a convex function, so these inequalities are fine. And so when I've written it this way, this is a complete set of implications. If u is more than or equal to max x1, x and 1, v is more than or equal to max y and 2, then this constraint implies this constraint. So I'm good. So that's two examples of things that might happen when you're first writing down a problem. And I'd say really a lot of the art that goes into optimization, there's one art that's even recognizing when a problem is convex. Well, there's one problem that's even stating a problem that can be formulated as convex. There's another art to recognizing it, and there's slightly less of an art and slightly more of a science of how you actually put them into parsers. Once you have something that you can prove is convex, it's usually the case that you can translate them into parsers that'll actually, into the language of whatever parser you want to use. So today, I'm going to talk about two examples from controls, robotics type things. The first one is going to be trajectory optimization. This example is pulled out of Russ Tedrick's manipulation class. So the credit goes to him. The second one is an example of attempting to land a spacecraft using controls. That example is going to be pulled from Boyd's additional exercises. A lot of those problems are very good. If you want practice with this, just go through that book. And then I'm going to talk about some classes other than LP that are kind of standard problems that'll come up that your parsers will be able to solve, and why recognizing those is important. I'm actually going to start with the rocket example because it's a little bit more involved, and since I only have 45 minutes, I'll start with that. Okay. Okay, so today's attendance survey code, by the way, is going to be controls. If you're in class, don't forget to sign the attendance form if you're taking this for credit. Okay, so we're going to take a toy example of, I've got a spacecraft that I'm trying to land on a certain launch pad. So the very simplified dynamics of this are going to be, is basically just very simple just F equals ma. So where I'm accelerating is just governed by F equals ma as a vector equation. We're going to assume this mass is constant for simplicity. Obviously, if you're trying to land a rocket, you're using a lot of fuel and your mass is going to be changing. That is something that you can include in the problem, but we're not going to because it kind of just obfuscates things a little bit. Okay, so the first thing I'm going to say is that I have some touchdown time. And at that touchdown time, I need to have touchdown. which means I need to be on the ground and not moving. My position velocity needs to be 0. The other thing is, the other assumption I'm going to make is that if this is where I'm touching down, I want to be in some cone. I want to be actually gliding in. One of the reasons for doing this is basically that we're going to linearize the dynamics, and so making sure that your rocket stays upright as you're trying to guide it down is very important. So there's kind of a glide angle constraint. So that means that, so there's going to be some glide angle constraint. We're going to use fuel at a specific rate. So the amount of fuel I use is going to be proportional to some gamma of t. Obviously, I'm going to have a max thrust. And the last thing I'm going to do, so that this plays nicely with convex solvers and makes things easier to write down, is I'm going to chunk up time. So I'm going to use a time discretization h. And I'm going to do what's called zero order hold. So f of t is going to be f of k. If t is in k minus 1 h k h. Basically, I've just cut up time. So in this model, what are my dynamics? Actually, I'll do something else. I'm also going to say given. So I'm going to be given some initial position and some initial velocity. Go ahead. This is just how much fuel I'm going to be using.
Oh, okay.
Yeah, it's just proportional to the norm. So yeah, it's some, if I want to produce a certain thrust vector, the norm of that thrust vector is basically how much force I'm producing. And so it's kind of like, the idea is power, right? If I want more force, I'm going to consume more fuel more quickly. Okay, so the natural, kind of a natural objective is we want to find the trajectory that gets me to the ground and uses the least amount of fuel, because rocket fuel is really expensive. So the first thing is, how do I write down my objective? I'm trying to minimize the amount of fuel. And the way I've set up the problem, how do I write down my objective? Okay, but I've cut up time, and this integral is some continuous function that's kind of a mess. So the way I write down my objective is I want to minimize the sum of the FKs. Those FKs are actually the thrust forces that I'm going to be producing at every discrete time step. Okay. Now, I want my thrust vectors to obey the maximum thrust constraint, right? Okay. So, first question I meant to ask, is this a convex objective? Can anyone tell me why it's a convex objective? We'll just do that.
The sum of convex functions is convex.
So the answer is it's because the sum of convex functions is convex. Is x minus x squared a convex function? No, it is not. But it's close, right? So I'm taking a non-negative weighted sum of convex functions. That's convex. Non-negativity there is very important. So this is a convex constraint. I'll just give you the glide constraint. Which will enforce that at every single time step, every single discretization time step, I'm within that cone constraint, where alpha is going to be actually defining the angle of that cone. So that cone constraint basically says if I want to be in a cone, again, the picture is this. If I want to be in this cone, then pk3 has to be more than or equal to this norm. And I'm actually assuming that I'm gliding to the origin. Okay, so let's see. I gave you the glide constraint. We've talked about the objective. Am I done? Someone shook their head. What's wrong?
You need the initial and final condition.
Okay, so I need the initial and final conditions. Good. So I'm just going to make capital K equal to the final, it's what, TTD over H. So my final condition is that, so I need to be not moving, and, sorry, I need to be at 0 and I need to be not moving. So that's the final condition. The initial condition is that P0 is equal to 0. V0 is equal to 0. Nope. Sorry. P dot 0. There we go. Now am I done? What's up? My forces should be positive. You're saying I don't want to flip the rocket over?
Or can you have a thruster that goes the other direction?
So the FKs are the thrust is a thrust vector, so there's no like positivity. It's just a direction that I'm going to push the rocket in.
But we're assuming that the nozzle could be pointed in any direction?
Yes. But that's a fair point. So the question was whether we can assume the nozzle will point in any direction. Yes, I'm basically going to assume that I can produce thrust, meaningful thrust in any direction I really need to. But you could add some constraint on that ensures that your rocket stays upright and that I'm only applying torques, or sorry, thrusts in certain directions. That's actually probably a very important constraint that you should include. So we're going to do thrust direction constraints. So this is probably important, but I don't have the equations for that offhand. There's one other set of extremely important constraints that we haven't put up there yet. My dynamics, yes. So if I don't put the dynamics in, what's going to happen to all of the intermediate vectors? To all of the intermediate steps? They'll all be zero because we're just going to go all over the place. So my dynamics are just going to fall out of basic calculus. Vkt plus 1 is equal to Vk plus h over m, Fk minus h g e3. And these fall out of just taking what happens with the zero order holds. Okay, so now I'm done. Now, so the reason I kept asking, am I done, am I done, am I done, is inevitably when you write down an optimization problem, you're going to write it down, solve it, get an answer back, and you're going to be so confused as to why it doesn't make sense. And always you need to keep in mind it's solving the problem you gave it. So that means, did I write all the constraints down? Am I actually asking it to solve what I want to? Okay, so we've talked about linear programs. Is this a linear program, first off? Yes? H is my time discretization step. H is my time discretization step. And then K is equal to TTD over H. Right, so if I want to land I want to land in 10 seconds, but I'm going to subdivide the problem into 1 millisecond steps or something like that. Okay, so this isn't a linear objective, but so this is not a linear objective, so already we're out of linear programming world. All my equality constraints, though, are linear, so we're good. We'll see that this is called a second order cone constraint. And this is the positive weighted sum of a quadratic objective. So we have a convex optimization problem. So what if I asked you to find the minimum time it takes to get to to actually descend? Go ahead.
Wouldn't that just be a function of, like, you don't
So the suggestion is to just compute it by calculating how much fuel you can expend at the bottom.
Yeah, because you know how much you have to decelerate, so it wouldn't be proportional to just expending as much fuel as you can at the end.
So it'd be
That's my answer.
So it'd be proportional to how much fuel you can spend at the end. That is possible. That sounds like a lot of work in a field I know nothing about. But I'm asking you to minimize something. We're in an optimization class. So the question is, can I replace this objective with minimize my touchdown time over h? Probably gonna have to take the ceiling of that because I want it to be an integer. So what's the problem with doing this in terms of, so the objective looks linear-ish. It's not actually continuous, but
There's many different aspects that contribute to time.
so the suggestion is that there are many different aspects that contribute to the time. Yes, but very importantly, so really it's a kind of a subtle thing. This value, which is equal to capital K, shows up actually in one of the constraints. And so actually the number of variables in this problem changes as the number K changes. That's not a convex optimization problem. It's a mess. But if you were to actually plot this function, or the solution to that, I think there's probably a pretty good chance that if we draw some cartoon of these are the variables, and this is the minimum time, there's some combination of the variables. It's reasonable to assume that this problem is going to have some unique minimum, right? So this problem actually falls into a category of problems known as quasi-convex. Which I'll get back to in a second. Quasi-convex is also called unimodular. These functions look like those. I'll talk about those in a second, but not all hope is lost there. But so the formulation of the minimum fuel was convex. If I change the problem just a little, I break everything. Okay, so let's talk about types of optimization problems. Let's do that. Okay, so obviously we've talked about linear programs. We've talked about very general convex programs. I also made a comment about how being convex isn't all that special in some ways because we need to be able to actually represent these problems on computers. In some convex problems, they're convex, but they're infinite dimensional, or they're equivalent to these very crazy things that don't give us hope that we can actually put them on a computer. So we do need to be able to have language or vocabulary about smaller class of convex problems that are still going to be powerful enough to solve problems we care about. So essentially, the problems that we can solve, the problems I'm going to talk about, they all fall under this category of conic programs because they're equivalent to intersecting a cone broadly defined in terms of some norm and an affine subspace. Those details are not really important. There are other programs that you can solve with other solvers. For example, like geometric programs and things like that. But we're going to talk about LPs, QPs, QCQP, SOCP, and then the first of the last lectures is going to be SDP, which is also a type of conic program. Nope. Okay, so we already know the definition of an LP. A QP is a fancy least squares problem. So a QP is just anything I can write these kinds of constraints in. It's a some sort of quadratic objective with some sort of quadratic objective, which I realize I'm not writing the most general quadratic objective. Where Q has to be a positive semi-definite matrix. Positive semi-definite matrix is one where all the eigenvalues are more than or equal to 0. These kind of problems show up a lot of time in errors and anytime you want to do any sort of least squares error tracking and things like that. But the ability to add these linear constraints makes it slightly more powerful than just least squares. The next one is a QCQP. That's going to be a QP but I'm going to let you do something a little bit more than just have linear constraints. I'm also going to let you have quadratic constraints. Thank you. They're just supposed to, I'm just trying to represent generically different things that could happen. So QCQP just lets me do with quadratic constraints. So this is the minimization, the feasible set of this is just the intersection of a bunch of ellipses, which makes really weird looking sets, and then some line. Yes, good point. So if the P and the Q are not positive semi-definite, so the question was, do the P's and the Q have to be positive semi-definite? The answer is yes, because otherwise they're not convex quadratics.
I have a quick question about that, like understanding that. Is it, like when there the intersection of those is definite, is this program so that you can also minimize when there's not a definite like intersection and it's just the closest to the intersection?
Sorry, can you repeat that question?
I was trying to understand what exactly it is, because you said it like an example of this would be the intersection of all those ellipses, right? And I was wondering if it would be just the intersection, which I feel like we could calculate directly, or if it's also like, for example, when there is no real intersection, but you can find the closest to it.
So this feasible set here, these sets right here, the some function is less than or equal to 0, some quadratic function is less than or equal to 0. This is the equation of some ellipse, and setting it less than or equal to 0 means that the feasible set is some ellipse. And then if I have a bunch of these, it's the intersection of all those ellipses. So without the equality constraint, it'd be kind of this region right here. But you're also allowed to have an affine equality constraint. And so the last one we're going to talk about is the SOCP. Okay, so last one is just the most general of these examples. That's the SOCP. So this is actually equivalent to a QP or a QCQP if you let the CI's be equal to 0. The way you see that is you just complete the square on this guy. And you can always write that quadratic as this right here. I'll just mention it. Be a little bit more formal about this in a few weeks. You have the SDP is the trace of so don't worry too much about SDP. Again, we'll talk about it later, but that's the last one. The reason so Boyd introduces SDP in his book at the same time as all these other problems. The reason for that is you kind of have the space of convex optimization. Somewhere in here you have cone programs. Some subset of that is SDP, SOCP, QC, QP, QP, LP. So I mean this Venn diagram very literally. Every LP can be written as an SDP. Every SOCP can be written as an SDP. There are ways to transform these functions up this hierarchy. So you might ask, why don't we just learn about SDP, get it over with? The reason is, with more structure comes more power to solve bigger problems faster and better. So you want to be able to roughly identify what function you're going to be in. And to take an example of why being able to identify is important, this is pulled off of the Drake solvers. Drake is a robotics toolbox that has a very, very good optimization parser in it. And if you're careful and write things as convex, it can actually recognize that. And it lets you use a bunch of different solvers. QP, SOCP, SDP. Okay. And so in it, you can use a very famous solver called Gurobi. It's state of the art, especially for mixed integer stuff, but it can not handle SDP. Mosec, another famous solver, can. If you use a solver called CLP that's available to it, well, the LP stands for I can only solve linear programs. But that solver is really good at solving linear programs. And so there are other examples, such as there's another famous one called OSQP that is designed specifically to solve very large-scale QPs at relatively low levels of accuracy. So the reason to know what kind of problem you have and to be able to have this vocabulary is once you've written the problem down, okay, what kind of problem do I have? Is this actually a reasonable problem to do? These are things that I personally do after I've written the problem down, and I try not to find an LP formulation. I try to find a convex formulation and then keep refining it until I get it down into something better and better. So a prime example of this is a prime example of why this could be important that someone mentioned to me yesterday was they were talking about a problem where they had some mixed integer variables. And in the original formulation, they needed some regularizer. And so the entire problem was actually a mixed integer linear program. And when you introduce the mixed integer property, you end up having to solve a bunch of these linear programs. One of the things that they did was someone added some L2 regularizer to it, changing it to not a linear program, which slowed down the problem a lot because all of a sudden, instead of doing MILPs, the specific regularization they used changed it from this to an SOCP. And mixed integer SOCP was much, much harder to solve. And so you could have just picked a different regularizer. L1 regularization, still linear. So there are these tricks where it's important to have this vocabulary and be able to actually think about these kinds of things. The last type of problem I'm going to talk about is quasi-convex optimization. Which I would love to find on here. So F is quasi-convex. Actually, before I start that, are there any questions before I keep going? Got about 10 minutes. Okay, so F is a quasi-convex function. If you can prove one of the following. So there are two equivalent definitions of quasi-convexity. I'm going to remove this. This isn't a good idea. You can either show that drawing a line between any 2-point evaluations ends up, if you pick, if F, yeah. I mean, I think these are self-explanatory, but it's basically the idea is that if I pick a point X and a point Y, and I draw the line between them, right? The point that this evaluates at is going to be less than the max of the two. If I evaluate at this point, if I evaluate at this point, I'm going to be less than the max of these two. Or it means that if I pick some line, alpha, and I want everything below it, the set of x's that give me values that are sublevel to that value is a convex set. So this is convex here. Go ahead.
So I'm almost kind of surprised to see the second definition because I thought some property like this was the reason we called it convex. Was why we use the word convex in the other to do things that are define things that are properly convex. It turns out that quasi-convex has this property that the level sets and the sub-level sets are convex. Is there some reason, like the naming makes sense to help me remember this?
So notice, so the question is, I think, a little bit of confusion about what the definitions are pointing at / trying to tell you. That's where I see the other board. So let's look at this carefully. I think you're confusing, and it's kind of a easy point to confuse, the difference between the sublevel set of the function and the epigraph of the function. So if I have some sort of quasi-convex function here, and I pick some alpha sublevel set, the alpha sublevel set is this chunk of line. But the epigraph of this function is a 2D thing. It's this area in here. Notice that the epigraph is not convex here. So f is not a convex function.
Okay, thanks.
It's a good question. Okay, so So quasi-convex optimization problem is one that I can write minimize f0 of x. Make these gi. So that's affine. This gets to be quasi. So this is, I'm trying to minimize some quasi-convex objective subject to some convex constraints. You might wonder whether we can make the quasi-convex constraints you might wonder whether we can have quasi-convex constraints. Basically what you do is if you have the constraint that f of x is less than or equal to t, this is quasi-convex. You can always find a function phi of t of x, which is equal to, so for example, this constraint is equivalent to defining a new function phi of t of x, which is equal to this function. This is a convex function, less than or equal to 0. This transformation is not really what's important. What's important about this class of problems and why I'm even bringing it up is that because of this property that I'm always going to be less than the max between the left and the right point, quasi-convex optimization problems can be solved using bisection search extremely efficiently. So the basic idea of solving this problem right here is I transform it into the problem of find x subject to this is kind of abstract notation, so I'm not going to do this necessarily. I'm just going to make this because these functions have this property of having this convex, the sublevel sets are convex sets. If I fix the parameter t, what I can do is I can now solve a convex feasibility problem, right? So this is a convex optimization problem. And what I can do is I can look over and just try to find this t and try to make this t as small as I possibly can. Even better, so first off, I said you could solve convex optimization problems quickly. And this is what I mean. This is actually very practical to do. Solving a polynomial number of polynomial time algorithms sometimes isn't the best idea, but this is actually extremely practical. Additionally, because of the extra structure, you can do what's called bisection search. So you pick some L and some U, some upper and lower bound, and you can basically just run this algorithm. You set t equal to the average of L and U. I should write this bigger. So you pick an L and a U. You solve this problem. And then 3, if feasible, well, then I know I can decrease the lower bound to t. Otherwise, I have to increase the lower bound to t. And then I break if u minus L is less than the tolerance. So this is another class of problems that you should be aware of that is not a convex optimization problem, but you solve it through solving a series of convex optimization problems. And I'll talk, well, the project document is going to be coming out shortly, but in the final project for this class, basically I'm asking you to find a problem where you use optimization at scale. And one of the ways that you can talk about using optimization at scale is using convex optimization as a subroutine for solving harder problems. And so this falls under the category of using convex optimization as a subroutine, which is, in my opinion, a good idea. Question?
I guess more generally, how well does this scale in terms of solving things that are nonlinear, like nonlinear dynamics?
So the question is, how does this scale in terms of solving problems that are nonlinear? A lot of people have a lot of definitions of what nonlinear means, so I'm not 100% sure what you're asking me with that. In terms of this scales well for solving problems you can write down as quasi-convex. What can you write down as quasi-convex? A lot, but not everything. So again, the picture I always have in mind of a quasi-convex function is something that only really has one bump in the bottom. Because if I come down, if I decrease in more than one spot, then I'm not going to have this quasi-convex property of having these closed compact sublevel sets that are convex. So it lets you solve slightly more general objectives, slightly more general constraints at the expense of having to solve more problems with fixed parameters and things like that. That's all I have.